Hello and welcome to lecture 24 of Math 2R03. In today's lecture, we're going to be looking at section 8.c of the textbook, where we're going to learn about characteristics and minimal polynomials. Now, characteristic polynomials are something that you would have seen in Math 1B03 or your first linear algebra course, but we're going to kind of define them differently in today's lecture. We're going to use kind of the eigenvalues and their multiplicities to define these polynomials. And the new thing that we're going to talk about is the minimal polynomials. And we're going to talk about kind of an important theorem which we may not have seen before, which is the Cayley-Hamilton theorem. Okay. Now, to kind of start off, I just want to point out that most of the results that I'm going to talk about actually hold over the real numbers, but we're going to kind of assume in today's lecture that we're only working over the complex numbers. Okay. Okay, so given that, what do we have? Let V be a vector space over our complex numbers, and let T be some linear operator. And suppose that we know what the distinct eigenvalues are, lambda 1 to lambda m, and we know the multiplicities of each of these eigenvalues. Then what we're going to do is we're going to make a polynomial from this information, and this polynomial is going to be z minus lambda 1 raised to the power of d1 times z minus lambda 2 raised to the power of d2, and then we go all the way down to z minus lambda m raised to the power of dm. And so we get a polynomial, and this is called the characteristic polynomial of T. Now this is kind of different than what you would have seen in Math 1B03. We actually use the determinant of a particular matrix to define this equation. And you can prove the two definitions are the same. And in fact, if you're curious, this should be done in chapter 10 of our book. But in fact, we're not going to do this in this course, okay? So chapter 10 is actually on determinants. So we kind of do things differently. This course versus the last, in this course versus Math 1B103. Math 1B03. In that course, we define determinants quite easily, and then we use that to define the characteristic polynomial. Here, we define eigenvalues and multiplicities first, and then we use that information to describe the characteristic polynomial. So just so you know that these two definitions are the same, it's perfectly fine that if you're ever trying to get your hands, on an actual characteristic polynomial, you can use the approach of Math 1B03. Okay, so what kind of properties does this polynomial have? Well, two properties here are very easy to prove. The first of all, what is the degree of this characteristic polynomial? It's going to be equal to the dimension of your vector space, and the roots of this polynomial are going to be the eigenvalues of the operator T. Okay, and both of these things kind of just fall out from the definition right here, all right? And it's because the degree of this polynomial is the sum of the multiplicities, right? And the sum of the multiplicities of the eigenvalues, we know from earlier in this chapter, is just simply equal to the dimension of the vector space. And for the second statement, we know that a particular complex number is going to be a root of this polynomial if and only if that number, when we plug it in, gives us 0. And the only way we're going to get 0 is if the lambda is equal to one of these numbers. So if and only if lambda is equal to lambda I for some I. So both of these things kind of fall out quite quickly. Okay, so I'll just state the Cayley-Hamilton, and when we come back after our short break, we'll actually prove this. So the Cayley-Hamilton theorem says that if you take any linear operator and you cook up its characteristic polynomial, and when you plug the operator T into that polynomial, so remember on this side here is what you're getting a kind of a new operator expressed in terms of the polynomial. What it turns out is that new operator is actually the trivial operator. It's the 0 operator. So we'll see the proof of this in a second, and I will take a short break here.